Hello, welcome back to the afternoon session. We'll start with four contributed talks, the first one being given by Matteo Bugli on the MHD Core Collapse Supernova code comparison project.
That was a mouthful. Thank you, Martin. Thank you, everyone, for being here. Thank you to the organizers for giving me the opportunity to share with you some of the results of the ongoing work we are doing, basically as a community of modelers of magnetic-rotational supernovae, to make what Bernard mentioned this morning, the huge pain of doing code comparisons, sort of sit together, start with a fair playing table of initial conditions and figure out whether or not we can agree quantitatively, or not just qualitatively, on the results and the estimates from these very, very complex models. So here you can see all the contributors to the project, and essentially, I will report some of the results we have obtained and some of the prospects in terms of upcoming results from new data that we are continuously acquiring. So I will not go too much into the details, of course, of the modeling. We heard from Bernard's lecture a very detailed and complete exposition of what modeling a circular supernova is all about. I will just focus on, once again, on the intricacy of having to deal with a lot of uncertainties and a lot of different conditions that define what a numerical model actually is constituted of. So first of all, we start with the uncertainties in the initial conditions. So we have to make a choice when it comes to a stellar progenitor, which comes with a certain core mass, certain history, a certain degree of mixing that has led to specific profiles. That also depend very much on the recipes over giga years of 1.5D modeling in terms of mass losses, transport of angular momentum, so on and so forth. And this also is encoded in a possible prediction for the rotation rate at collapse, which very much depend on these recipes. So these, for practical reasons, approximation that allow a modeling over these large time scales, but that have to deal with inherently multidimensional 3D phenomena. So rotational rate and magnetic fields, these are things which are extremely challenging to model in such conditions. And so this is where the uncertainties stem from in terms of what do we start from when we start describing the collapse of a massive star. And then we also have the impact of the perturbations that are already in the progenitor before the collapse. So the turbulence and the small scale dynamics that can have a quantitative impact on the explosion itself. On top of that, then, in a numerical model, we want to define what are the physical ingredients that we want to put into it, and more specifically, how we decide to approximate them. So we know that we have to deal, of course, with self-gravity, and there are different choices, mainly two. There are sort of different compromises when it comes to the accuracy and the efficiency of the code, that is from full GR, numerical relativity, to pseudo-Newtonian approach, where we apply corrections to a Newtonian potential. Then, we want to define what is our weapon of choice for the neutrino transport. The state of the art is sort of settling over schemes just like, for instance, like the M1. Of course, there are different choices which are maybe more efficient, that allow a more prolonged modeling. But this is something that it's not homogeneous to the landscapes of numerical models. And then, last but not least, of course, we want to decide how we describe the high dense nuclear matter that it's basically describing the most important part of this model. So the central engine, the compact objects, the proton-neutron star, and uncertainties, needless to say, are there as well. And so a choice has to be made for every model that is produced. So this is progenitors, physical ingredients. On top of that, then there are the specifics of the numerics. We have to decide which kind of grid we want to use, basically whether a Cartesian-like or spherical grid. We need to define whether, for practical reason, we need to refine some of this grid along, for instance, close to the geometrical singularities or with AMR refinement levels. And then it comes down to how we solve, for instance, the magnetohydrodynamic equations. So when it comes to the nitty-gritty details of Riemann solver, interpolation routines, which are connected inevitably to one of the most limiting factors that was mentioned at some point this morning, that is resolution and numerical dissipation, which is, again, a limiting factor that is very difficult to control, because all these ingredients, when it comes to the specifics of how we approximate our models, they can contribute to define a certain dissipation, and therefore that makes it difficult to pinpoint exactly a value for this. So once this is out there, the main question that is driving essentially any kind of comparison is, can we reproduce consistent results? Can we agree on an initial setup, and then to what extent can we reproduce exactly the same dynamics and quantitatively the same calculations? And see, of course, Bernard's lectures and slides to have a another view on the problems. So there have been some, in the recent years, some attempts at quantifying this agreement, or sometimes lack thereof, between numerical codes. And the focus of different code comparison has shifted from, for instance, the impact of the neutrino transport scheme. Of course, this is of paramount importance when it comes to standard neutrino-driven calculi supernovae. And so there are works that are dealing with one-dimensional, two-dimensional, and 3D studies. There has been, in 2018, a systematic study of a number of 3D hydrodynamic codes with different choices for the rotation, gravity, neutrino transport, which basically have agreed on the fact that things are not too bad, are not looking too bad. On a quantitative level, there are some deviations, but more often than not, this study show that at the early times, there seems to be like an actual convergence and agreement among different codes. And for hydrodynamic standard explosions, essentially every phenomenon that has an impact on how the proton-neutron star compresses, how the neutrino heating efficiency may modulate, then you will inevitably have an impact on your numerical model, because you're tricking with the neutrino fluxes, you're tricking with the efficiency of the heating mechanism, and therefore you can have a deviation from the mean. This talk is not about regular calculi supernova, as the title suggests, but it's about extreme explosions. So the magnetorotational explosion mentioned this morning. And these are explosions that, in a nutshell, essentially describe the most extreme phenomena and transients that either exhibit exceedingly high kinetic energy in the ejecta, so typically associated to events such as rare hypernovae or gamma ray bursts, or they have exceedingly high luminosities, up to a factor of 100 compared to regular supernovae. So that is the case, for instance, of superluminous supernovae. And the main two ingredients that essentially are at play for this kind of sources that justify such a energetic budget that neutrinos cannot provide is a combination of strong, large-scale magnetic fields and fast rotation. And this is at the core of the magnetorotational mechanism, essentially rotation providing an energy reservoir in the core that would not be there otherwise in a non-rotating progenitor, of course. And magnetic fields that needs to be there at the same time to provide a way to tap into the energy, because otherwise it would just be retained by the core. It would have an impact in terms of producing possibly a centrifugally aided neutrino explosion. But without large-scale magnetic fields, the bulk of the energy is just not going to help the explosion mechanism itself. And we know now, since almost 20 years, that we can reproduce numerically these bipolar outflows from such extreme conditions of fast rotation and strong magnetic fields. Watch out for Lyubov's poster that is going to be presented fresh out tomorrow, and also a couple of talks by Martin and Gerardo tomorrow talking about exactly this kind of modeling and sources. So I mentioned rotation, magnetic fields. When it comes to their origin, rotation is something that inherently needs to come from the progenitor as a consequence of basically the lifetime of the massive star. But magnetic fields, their origin is even more uncertain because having at the same time fast rotation and strong magnetic fields, it's not an easy task just because one of the many things the magnetic fields do very well is just get rid of that rotation, that angular momentum by magnetic transport. So there are several suggestions as to how these magnetic fields can be there, when we need them and where we need it to produce these explosions. I'm on the suggestion of having fossil fields from the progenitor or having the outcome of stellar or previous stellar mergers. One promising scenario is constituted by proton-neutron star dynamos. So dynamo processes that occur during the explosion itself, within the PNS itself, which are driven by phenomena such as the convection in the PNS or the magnetic rotational instability. And the dynamos have some studies, recent studies show that they can, in effect, produce strong, intense magnetic fields. They can, to some extent, also produce large-scale magnetic fields. And essentially, this is where still we need to work in terms of assessing how does the magnetic field look like. And but we know that in principle it can be done. So probably the first good comparison has been done. This one in 2D was provided by Vishnu Varma and Bernard and Martin, and they basically took popular progenitors, 35OC, and they reproduced them with two codes, coconut and Osaka. And they already show that in 2D, there is definitely a qualitative agreement in terms of what the codes can do. You can see here, for instance, the shock propagation over time, and then the ejecta diagnostic energy. There are definitely some deviations between the two codes, and they also did it for an explosion with much weaker magnetic fields. So there is a trend of different codes similarly provide qualitatively similar scenarios, but we wanted to extend the amount of models, extend the number of codes, and most importantly, go to 3D because it's an absolute necessity. So this is a table of the codes that so far are involved in the comparison, and you're familiar with, I'm pretty sure, basically all of them. And you can see basically the diversity that we have in terms of grid geometry, in terms of neutrino transport treatment, the dimensionality of the models they provide so far, and the treatment of gravity. So unfortunately, today I cannot show you anything from GRMX, which is so far the only full GR code, because models is still running. So Philip Musta has assured me that this is going to be something by the end of the week. I trust the guys. So I mean, stay tuned for some more results on that. But one of the important things is essentially the settings that we impose as to be as far as possible. We, of course, set a common equational state, and importantly, we set also homogeneous, like consistently through the code, non-asymmetric perturbation to essentially trigger in a sort of similar way non-asymmetric mode, specifically thinking about what could happen for instance, the development of the kink instability in the jet. I will go a bit fast through the initial condition. Essentially, we landed on popular progenitor, S20, 20 solar masses with solar metallicity. This progenitor has no rotation, no magnetic fields, but what we did was put them by hand. So we have a rotation rate which is constant within the first 1,000 kilometers, and then a decaying law that describes a constant specific angular momentum distribution, which is rather common in the literature. On top of that, of course, a magnetic field. So once again, we have in internal 1,000 kilometers magnetic flux, which is essentially constant, uniform, and then we have a dipolar-like decay. So we have essentially a modified dipole in the initial configuration. So here I'm flashing the results for the shock propagation and the ejecta energy for different models. So here, I don't know if you can really see the labels, but essentially we are dealing with both 2D and 3D models. The two extremes are the 3D realization with Anos Alcar, and in purple we have the 3D model of the Japanese group. So already we can see that for all models, we're sort of less triggering a prompt explosion. There isn't much stalling, but there is definitely a variance. There's definitely a quantitative deviation in terms of how efficient the explosion occurs. And that goes, of course, also for the energy. And as for the 2D versus 3D question, there is something interesting happening here, because in nanonuclear we have systematically more efficient explosion in 3D, whereas, for instance, in the Japanese group, that seems not to be the case. But of course, we need to collect more data and sort of try to figure out a bit better what is happening here. So this is an animation of three, so the column-wise, you have three models, nanonuclear at low resolution, and then two simulation with flash, a low and high resolution. You will see on top the ratio of magnetic to thermal pressure, and on the bottom where we have the specific entropy. So this is to show you what the explosion kind of looks like. This is the prompt explosion with nanonuclear on the left, very almost axisymmetric in a sense that it's very fast, whereas for flash, lingering a bit behind, and most importantly, we have a much higher degree of non-asymmetries. The explosion, the ejecta are still pushed, and with also a higher magnetic to thermal ratio of the pressure, but it's definitely struggling a bit compared to the nanonuclear case. And unfortunately, the high-resolution model, being high resolution, it's lagging behind. It's just froze because the data is not there yet. If we take a closer look at smaller scales, then we can appreciate even a wobbling of these the base of the outflow in the case of flash, which is not very much there for light curve. So another representation of the different degree of asymmetries in the models. And we took the diagnostics suggested by Philip in 2014 for the kink. And in terms of these diagnostics, things do not seem to be quite different between codes, but we actually saw the differences. So in a sense, we probably need to refine our way to characterize this instability in order to be more sure about what is the deal with these different codes. Because as far as this displacement of the barycenter goes, at 100 kilometers, it increases exponentially, but then it saturates. As for the proton neutron star, things are looking relatively good in terms of the mass. Moment of inertia is a bit different for the flash, but increasing resolution, it seems that this bump is alleviated. In terms of toroidal distribution of energy, rotational energy and magnetic energy, there are quite differences. And essentially, we're looking at a different way the codes and these models had to tap into that rotational energy, and also the way that the magnetic fields can slow down the proton neutron star. This is just a slide showing that profiles are looking spatially relatively good, but I definitely want to spend a couple of minutes on gravitational waves. Of course, we are starting to collect this data now, and you're looking here at the very early distribution of the strain for the flash and the nanonuclear code. So in terms of the bound signal, the agreement is pretty good, but then it starts deviating quite a bit the longer we go. So now I'm enlarging the axis of time, and you can see that there are differences arising between the codes. The A+ at the equator seems to be lasting more similar to the codes for longer time, but as we continue, essentially, we start appreciating different amplitudes, different frequencies, and essentially then we have, if we follow them long enough, that memory signal due to the non-axisymmetric expansion of ejecta. So we need to probably have more data, longer simulations to characterize it better. I will leave you with my conclusion. Essentially, I will not go through much once again. We need to do definitely more and more multi-mechanism analysis. We will see, for instance, Shota's talk tomorrow about that. Just as more advertisement, early next year, I will start a URC project at CA Cyclase. So in the upcoming months, I will try to build a team. So if you're interested, or if you know students or postdocs, please don't hesitate, come talk to me. And with that, I thank you for your attention. Get any questions?
Well, thank you very much. There is time maybe for one or two quick questions. No.
Yes. Thank you. Thank you, Matteo. For the flash, when you plot the explosion energy for flash M1, it seemed to rise and then fall and then rise again the first 100 milliseconds. And then when you play the movie of the, like right there, that brownish line, it rises then falls. And then when you play the movie of the jet formation, it seems like there's some fallback of the jet and you mentioned it's a bit more oblate. I'm guessing those are related. Is this because, is flash a Cartesian code here? Okay, that might be why then.
Yeah.
Okay.
So, yeah.
That's it.
Okay. Yes. Come again?
You think it's because it's a Cartesian code?
That's definitely some of the.
Then you can also worry about the polar grid, which also has some specific direction. So I would be very cautious concluding that one code has disadvantages more than the other code. My question is about the bounce signal. I was astonished about the good agreement between the codes. Is the microphysics you use for a collapse phase has it been coordinated so that all of you use the same electron capture rates during collapse, or is it because there is sufficient rotation to determine the signal more than the core mass, the inner core mass, which depends very much on the electron capture physics?
I think it's pretty much a combination of the two. In this regime, I would not expect maybe those rates to have such a quantitative impact. But I think instead of electron capture rate, we are basically sharing among not just Flash and Osaka, but the other codes as well. We are quite homogeneous in that respect. The differences in the neutrino emission, but as far as this goes, the signal, I think it's basically the fast rotation, which is helping us.
Okay. Very.
So we were talking before about the high frequency feature, and that one you need to have the spectrogram. I guess you didn't run it long enough to see if it develops, right?
Right. We have some. I have a slide with a tentative spectrograms for these models. It's yeah, it doesn't say a lot. For instance, in Alcar, we didn't follow the whole bounce sufficiently earlier to have the signal. So in a sense, we have some hints at the low frequencies there, but yeah, not there yet.
Very good. So let's thank Matteo